Hello, everyone. Welcome back. In this section, I will be covering section 2 of chapter 6, which is volumes. In early section 6.1, we saw to find area between two curves. Even though we know that integral is all about finding the area under a graph of a function, we actually use the application of integrals in finding area of the region bounded by two curves and then area between two curves in the last section. In this section, we are going to be seeing methods. One of the two methods to find the volume of a solid of revolution. We will use calculus to give an exact definition of volume. A simple type of solid known as a cylinder is shown in figure 1a. So look at this figure 1a. It is bounded by a plane B1, which is the base, called the base, and the congruent region B2. So there is a base B1 and there is another congruent parallel base, which is B2, in a parallel plane. The cylinder consists of all points on line segments perpendicular to the base and join B1 to B2. In general, if the area of the base is A, and the height of the cylinder is h, the volume of the cylinder is base area multiplied by height. So this is in fact true even if you consider a rectangular box. For a rectangular box, the volume we define is L, length, width times height. If you notice, it's L times W is nothing but the base area, which is the area of the rectangular base, times height. So it will be satisfied for any type of cylinder. So in the case of a circular cylinder, which is the second one, the area of the base times height, the base is a circle, so its area is pi r square multiplied by h, which is the base area, which is pi r square multiplied by h. So that is the area of that cylinder. For a solid S that is not a cylinder, so now we are going to see how we can find out the volume if it is non-cylindrical. So we are going to make them into smaller cylinders. As we know the volume of a smaller cylinder, and we are going to apply that to find the volume of any figure which is not actually a cylinder. We are going to divide them into thin slices of cylinders. That's the idea of the volume for any given solid. For a solid S that is not a cylinder, we cut S into pieces and approximate each piece by a cylinder. We estimate the volume of S by adding up the volumes of these cylinders. Start by intersecting S with a plane, giving raise to a cross section. Giving raise to a cross section of the solid S. Let A of X be the area of the cross section S. So look at this picture. This is the solid. Now we are at X, you are taking a cross section, and the cross section is a cylinder, right? So the base area is A of X, and the height is the thickness of the cylinder. Area of the cross section in the plane P of X perpendicular to the X-axis and passing through the point Ex. And X lies between A and B. So you're imagining the prototype of the solid in the interval A to B in two-dimensional. Okay, so we are making a cross section at the point X, And then the cross section is the shape of a cylinder, which has the base area A of X. So we call A of X to denote the area at the point X. And A of X is the area of that cylinder, small cross section. And the thickness is the thickness of that cross section. So divide S into number of partitions n slabs of equal width delta X by using the planes P of X1, P of X2, etc. to slice the solid. If you choose sample points xi star and xi minus 1, xi minus 1 xi, which is the ith interval, we can approximate the ith slab Si by a cylinder with base area A of xi and height delta X. So the idea of finding the volume for any solid is similar to finding the area of the cylinder and adding up the cylinders. So we are going to use the technique of Riemann sum here. So just as the way when we did area under a graph of a function, if we have to find out the area under a graph of this function f of x, bounded by the lines x equal to a and x equal to b, we use the technique of Riemann sum. We divided this interval into number of partitions, and we considered the ith subinterval, and then we considered rectangles in each of these subintervals, and then we added all the areas of these subintervals, all the areas of these rectangles. So similarly, so by adding all the areas of these rectangles in each of these subintervals, we get and then we allow n to approach infinity, the number of partitions, number of intervals to increase to infinity, then the sum of these areas will be approximately equal to the area under the graph of the function. Exactly similar idea of the Riemann sum, we are using it to the volume. Here the area is length times width, the height of the rectangle times width of the subinterval delta x. So it will become f of xi times delta x in each case. That will be the area of one rectangle. And we will do that for all the rectangles. The same way in this particular case, when we consider the volume of the solid for this figure, we are going to consider the volume of the cylinders that we make between A to B. So how do we get the cylinder? So by each partition point, each interval will give rise to a thickness delta x. In that, we will form a cylinder in each subinterval. That cylinder will have the base area A of x. So if it is placed at x, it will have the base area A of x and thickness delta x. So area times thickness will give us the volume. So we are going to find out for each volume, each slab that we made here. Look at this picture. For each partition point, so this is the first figure in that first interval, and we have the second interval, and we have that second cylinder there, and then third interval, third cylinder, and so on. For each one of them, we are going to find out the area multiplied by the thickness for each of those cylinders. And we add them all. So volume of the slab Si is A of xi star times delta x. So A of xi star is the area, base area, and delta x is the thickness. So we do this for every slab, and we will be approximately equal to A of xi star times delta x, I varying from 1 to n, and we will allow n to approach infinity. So definition of volume. Let us be the solid that lies between x equal to a and x equal to b. The cross-sectional area of S in the plane P of x through x and perpendicular to the x-axis is A of x, where A is continuous function. Then the volume of S is given by V equal to limit as n approaching infinity sigma I varying from 1 to n A of xi star delta x, which is the Riemann sum is big sum, Riemann sum is a big sum. Big sum is usually denoted by an integral, elongated as. So integral a to b ax dx. So volume of the solid is integral a to b ax dx. Okay. Let's take an example here. Find the volume of the solid obtained by rotating about the x-axis. So what curve it is made up of, rotated about what axis is important. Axis, the region under the curve y equal to square root of x from 0 to 1. Illustrate the definition of volume by sketching a typical approximating cylinder. So in every volume problem, what you have to remember is that what are the things that are important to us? Important. What are the three information that are important in the volume problem? Okay, the volume problem. What are the things that you would pay attention to? What is it? What is the curve it is made up of? Which curve you are rotating? It is bounded by what values? Bounded by what values? Is it x running from A to B or y running from C to D? Is it y bounds given or x bounds given? And the third one, what is it rotated about? Is it rotated about the x-axis or the y-axis? So you have to know these three information. Right? So find the volume of the solid obtained by rotating about the x-axis. So we need that information. Under the curve y equal to root of x from 0 to 1. So we have the curve bounds 0 to 1. The bounds are for x. Illustrate the definition of volume by sketching a typical approximating rectangle. So here shown square root of x, and it says 0 to 1. So if we are interested only from the value x equal to 0 to x equal to 1, and we are going to rotate this curve about the x-axis. So when you rotate about the x-axis, you get a figure like this, a cup inverted, a cup like this, which is facing the x-axis like that. And then what we are going to do in this process is that between 0 through 1, we are going to divide the interval into number of partitions. So this is x equal to 0 and this is x equal to 1. We're going to divide this into number of sub-intervals. And we know that x0, and this is x1, and so on. On the disk xi, on the sub-interval, xi minus 1 xi, which is the ith interval, we make a cross section. This is in the form of a disk. Okay, so in the cross section, so this is in the form of a cylinder. In this case, it is also a disk, and area of the disk. So if you consider the area of the disk, is it's pi r square. Because it's a circular one, it is pi r square, where r is the radius. So it is pi radius is equal to this distance, which is, so the disk is placed at the distance x from the origin. So let's consider first. So consider a cross section which is a disk at the x, at x from the origin. So A of x is the area of the disk, which is pi times, if this point is x and the y coordinate is the radius. So this point is x comma y. So what is the radius of the disk? Which is the y coordinate at the point x, which is equal to y. So it is, radius is y squared. So I'm substituting for the radius. Radius is y. But what is y equal to in this case? Y equal to square root of x. Square root of x the whole square. Okay. Y equal to square root of x. Square root of x the whole square, that is pi x. So ultimately, area of x becomes a function of x. So anytime you rotate about the x-axis, the integrand that you evaluate will turn out to be a function of x. And step 2 is to use the formula to evaluate. Use the formula to evaluate the integral, to evaluate the volume. So what is the volume formula? Integral a of x dx. X running from 0 through 1 in this case, which is given in the problem. So it's x equal to 0, x equal to 1. That is integral 0 through 1. A of x is pi x and dx. So pi is a constant which can be pulled out. Integral of x, which is x squared over 2 between 0 and 1. So it is pi times 1/2 minus 0, which is pi over 2. Okay. So volume of the solid, in this case, is half of pi units cube, because it's volume. In this problem, the method that we used to find out the volume is known as the disk method. It's known as the disk method. So you're going to see 3 methods of finding volume. The 3 methods are, 3 methods of finding volume. One is the disk method. The second one, washer method. And these 2 are covered in this section. 3 is a cylindrical shell method. This is done in the next section. So when we slice, we get a cross section of a disk. That's why it's called disk method. So let's try another problem where the rotation is about the y-axis. Find the volume of the solid obtained by rotating the region bounded by y equal to x cube, y equal to 8, and x equal to 0 about the y-axis. So what is it? What is the curve we are using here? Y equal to x cube. What is it bounded by? Bounded by y equal to 8 and x equal to 0. X equal to 0 is the equation of the y-axis. So it is bounded by the y-axis and also y equal to 8. Then it is rotated about the y-axis. Rotated about the y-axis. So these 3 things are important in this problem. Now, so the y equal to x cube graph is shown here. Even though the graph goes all the way below, because of the other information that is given here, so it is bounded by the line y equal to 8 and the y-axis. So for now, we are considering only this part, the upper part of the graph, and it is rotated about the y-axis. So when you rotate this curve, this region about the y-axis, what you get, when you rotate this curve about the y-axis, you get an upward curve, like vertically upward, open upward curve, which can hold water kind of curve. So now we are going to make a slice or a cross section at a distance y from the origin. So we are making a slice at a distance y from the origin. So this distance here is y. So at a distance y from the origin. So the horizontal distance there is x comma y. So suppose you take a point x comma y on the graph, the horizontal distance would be x. Why do we need the horizontal distance? Because we need the radius of that disk. So let's consider what we are also going to do between 0 to 8, because the whole thing is to be done between 0 and 8. From 0 through 8, we are going to divide into number of partitions, number of subintervals, and you are going to consider a cross section on the ith subinterval. So you are imagining this particular disk over here in the ith subinterval. So first step, consider the disk, consider the cross section. It's a disk at a distance y from the origin. We saw in the earlier problem at a distance x from the origin because it was rotated about the x-axis. Now this is rotated about the y-axis, so we consider a rotation vertically. So we are going to consider the rotation about the y-axis. So at a distance y from the origin. So if you take a point xy to lie on the circumference of the circle or the disk, then the horizontal distance x would be the radius of the circle. Then x is the radius of the circle, is the radius of the disk. Now we call A of y, which is the area of the disk, which is pi radius square. Pi, the radius is nothing but x here, x square. So the radius in this case is x. But we know that because we wrote that as A of y, everything must be turned in terms of y. What we have is x square. So what is x in this problem? So we are given the curve y equal to x cube, correct? So y equal to x cube. So if you take the cube root on both sides, so cube root of x cube, we get x equal to y to the power 1/3. X will be y to the power 1/3. So if we use that, A of y, the area of the disk, is pi, x gets replaced by y to the 1/3, and you have the square for x. So I'm just substituting for x in terms of y. So it is pi y to the 2/3. Right? So A of y is pi y to the 2/3. Now, step 3 is to evaluate the integral, evaluate the volume. Evaluate the integral to find the volume. So volume is integral A of y dy. Y in the problem is running from y equal to 0 through y equal to 8. Right? So y runs from y equal to 0 to y equal to 8. That is integral 0 to 8. The purpose of writing this as A of y is, remember that whenever you are integrating with respect to y, the integrand must be in terms of y. So what is the area of the disk here? So pi y to the 2/3, then times thickness dy. So it is area multiplied by thickness becomes the volume. And you are doing that for every cross section. So starting from 0 to 8. So the entire volume gets covered. So if I integrate this, integral that to pi can be taken out. So y to the power 2/3, 2/3 plus 1, so which is 5 over 3 divided by 5 over 3 between 0 and 8. So it is 3 pi over 5. Then if you substitute 8 to the power 5 over 3, upper limit minus lower limit. So it will be 3 pi over 5. Then 8 can be written as 2 cube. So 2 cube to the power 5 over 3. So that will be just 2 to the power 5, which is 32. So 32 times 3, which is 96 pi over 5. So the volume is 96 pi over 5, that many cubic units. You can either say it's cubic units or you can say units cube. So note that in the first problem, when it is rotated about the x-axis, everything turned out to be a function of x. The integrand turned out to be a function of x. In the problem where it is rotated about the y-axis, the integrand turns out to be a function of y ultimately. Let's try a problem based on washer method. What do you mean by washer method? When do you apply washer method? So the region R enclosed by the curves y equal to x and y equal to x squared is rotated about the x-axis. Find the volume of the resulting solid. So now you see the first curve y equal to x is drawn as a line, which is a straight line, and then y equal to x squared, which is a parabola. Now, even though both can be extended further, because we are now finding this particular region enclosed by these two lines rotated about the x-axis. So we are interested what the point of intersection are. So step 1 is to find the point of intersection. So in this problem, it tells you it is 0, 0 to 1, 1. Suppose you get two curves where you do not know where they intersect, and this is the way you want to solve, okay? To find the points of intersection. Y equal to x and y equal to x squared. So set the two y's to be equal. So x minus x squared equal to 0. So x times 1 minus x equal to 0. So x equal to 0 and x equal to 1. So these are the x coordinates of the point of intersection. So if you substitute them in y equal to x, so substitute them either y equal to x or y equal to x squared, you get y equal to 0 and y equal to 1 also. So you notice x, y, 0, 0 and 1, 1 are the points of intersection. So which is what's shown in the graph here, 1, 1 and 0, 0. It's already shown. So you have this particular region and we have to rotate this about the x-axis. This has to be rotated about the x-axis. The difference between the problem that we did earlier and this particular problem is that when you rotate this about the x-axis, you notice that there is a gap. So if you get the figure like this, and you definitely see there is a gap between the region and about the line about which the region is rotated about, in this case, x-axis. So what you get when you make a cross section as before, you're going to get a ring, kind of a washer, then which has an outer a rim and also an inner rim. So you're going to get some kind of a donut or some kind of a washer or some kind of a tire where you have an outer rim and an inner rim. So you're going to get two concentric circles with a hole in between, and then you're going to have the outer one will correspond to y equal to x, the outer curve or the top curve. In this case, it is y equal to x, and then the lower one corresponds to y equal to x squared. So this concentric circle, so this is, if you consider only the cross section of the washer as shown in here, in the third picture, it has got the outer radius, which is equal to x, which is x, and then you have the inner radius, which is x squared. So that's how you get two concentric circles or a washer. So we have to just tweak the problems that we did in the first two. So remember that in step 2, we are going to find out the cross section and its area, right? So make a cross section at x is a washer. So area of the washer we call it A of x because it's ultimately the rotation about the x-axis. So it is area of this particular one is pi outer radius square, area of the outer circle minus area of the inner circle, right? Area of the outer circle minus area of the inner circle. Minus area inner. Both are circles. So pi r2 square minus pi r1 square, where r2 is outer radius, in this case it is x square, pi inner radius, that is x2, x square, the whole square. So pi outer radius square minus pi inner radius square is the area of the washer. So A of x is area of the outer circle minus area of the inner. Both are circles. So it is pi r2 square minus pi r1 square. So pi outer radius is from outer radius. So it is from the center to the upper curve. So from the center to the upper curve. So it is y top square minus y bottom square. Among the two curves, the outer one will be the top curve. Top y written as a function of x. So this is equal to x. So pi, what is y equal to? The top curve. The top curve is y equal to x. So x square minus pi. What is the bottom curve? Y equal to x square, y bottom. So that is equal to x square, the whole square. In both cases, you take only the y coordinate, which is written in terms of x though. So it is pi x square minus pi x to the power 4. So what is the thickness of the washer? Thickness of the washer is nothing but delta x, because it is placed at the ith interval. So all intervals are of same thickness. So it is equal to delta x. So the volume of the washer volume of each washer equal to A of x times delta x, right? So A of x is pi x square minus x to the power 4, that is A of x, times delta x. Now we are converting all of this into the integral. So we are going to do that for every x between 0 through 1, right? Step 3, evaluate by using integral. So volume is integral 0 to 1, a of x, and then you know that delta x would become dx in the integral. It's integral 0 to 1, pi times x square minus x to the power 4 dx. So pi can be taken out. Integral of x square is x cube over 3. Then integral of x to the 4 is x to the power 5 over 5 between 0 and 1. So it is pi times 1 over 3 minus 1 over 5, and then lower limit solves 0. So it is pi, 5 minus 3, so 2 over 15. So it is 2 pi over 15. Because it's volume, it's units cube or cubic units. You can write like that. So in this problem, we have a typical washer, and we have given the picture already given here. In the earlier problem, one thing we may want to add is that we found the area of each slice, each disk, and the volume will be nothing but the area times thickness, area multiplied by thickness. So that is what the area of the cylinder is. So pi y to the power 2 by 3. Now the cross section is made along the y-axis. The thickness would be delta y, which becomes dy in the integral part. So when the question is also asking you to graph the typical washer or disk. So in this case, that is shown in the picture itself, a typical washer, typical disk. In the earlier problem, typical disk is shown in the picture itself. In this problem, the third one, the washer must be shown like that. So in every problem, make sure you show the typical washer or a disk which is used to evaluate the integral. Let's do one problem from this set, and then the rest of the problems are done in another set of videos, or I'll make another video to show these some of the other problems. So let's try in this video. This is part 1 of section 6.2. So let's try problem number 2 here. A problem number 13 here. Let's do problem number 13. Y equal to square root of x minus 1, y equal to 0 and x equal to 5 about the x-axis. What is the general instruction in the problem? Find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, and a typical disk or washer. In problem number 13, it's also one of the practice exam questions. Y equal to square root of x minus 1 is the curve, and it is bounded by y equal to 0. That what does it mean? It is a x-axis, and x equal to 5, and it is rotated about the x-axis. So we have the graph y equal to x square root of x minus 1, y equal to 0, which is the x-axis equation, and x equal to 5. And this region is it's rotated about the x-axis. So it is rotated about the x-axis. It's rotated about the x-axis. You get a figure as shown on the right, and we are going to make a cross-section perpendicular to the x-axis. Cross-section at a distance x from the origin. So the cross-section would look like a disk. So it's a disk method. Make the cross-section of a disk at the distance x from the origin. Also note that square root of x minus 1, you can of course use your graphing calculator. It is actually square root of x is this graph, and then square root of x minus 1 is a right shift 1 unit. So if it starts at the origin, this one will start at 1. So square root of x minus 1. You can also use your graphing calculator to check this. And remember that it is bounded by x equal to 1 to x equal to 5. So we are interested only in that part of the region between 1 and 5. So at a distance x from the origin, so we have to find out the area of this disk. Because it is rotated about the x-axis, I'm going to write a of x pi, because it is a disk, it's pi times radius square. Pi times what is the radius? Y, vertical distance. But what is y equal to in the problem? Y equal to square root of x minus 1. So that is being squared, right? So y is square root of x minus 1, that is squared. So which is equal to, that is, of course, that is a radius as well. So now square of a square root, they get cancelled out. So pi times x minus 1. So that is a of x. Now, what is the volume of the disk? Area times thickness. Area times thickness. What is the area? Pi times x minus 1. Thickness is delta x. This is as far as this sample disk at a distance x from the origin. We are going to do this for all the disk running from 1 through 5. So in step 3, we are going to evaluate this integral using integral notation. Evaluate the integral to find the volume of the solid. So volume volume is integral 1 through 5 a of x dx. The delta x in the Riemann sum will become dx in the integral. That is 1 through 5 a of x, which is pi times x minus 1 dx. So pi can be taken out. Integral of x is x squared over 2. Integral of 1 is x between 1 to 5. So it is pi times 2 square, the 5 square, which is 25 over 2 minus 5. That is for the upper limit. And for the lower limit, it is 1/2 minus 1. That is pi times 25 over 2 minus 5, minus 5. So minus 1/2 minus 5 plus 1. So if you distribute the minus, that is pi times 25 minus 1, that is 24 over 2, which is nothing but 12, and minus 4. So it is pi times 12 minus 4, which is equal to 8 pi. Because its volume, we will write that as units cube or cubic units. Hope this video helps. So watch my next video for some more problems of this section, which is part 2 of the video.